Welcome to Code Rage 5. I want to thank Embacadero for inviting me to speak. My name is Gordon Morrison. I'm the inventor and author. This slideshow presentation is about a technology based on temporal engineering. My examples are implemented with Delphi. This presentation is about technology. I will cover the traditional approaches, my solution, quantify the differences, and be available for questions at the end. This presentation is based on the technology in my patent. I've made this patented work freely available. Anyone can use this technology. The patent is U.S. patent number 6345387. It issued February 2002. You can download the patent from the patent office. The last time I did that, it cost $3. This technology is also described in my book in more detail. The title of the book is Breaking the Time Barrier. This is significant new technology. If someone tells you that it's not significant technology, then tell them to prove it through the following challenge. I created this challenge because in every presentation, there's always someone that wants to challenge my approach. If you think you have a better way, now you can prove your approach by completing this challenge. Using your temporal spatial if-then-else approach, produce a 5-function calculator. Add, subtract, multiply, divide, and percent. The specification is available at www.vsmerlot.com. Count the number of if-then-else and case default statements, that is, count every logic decision point in your application. Don't use my temporal approach. Computer science is nearly 60 years old. Since the beginning, we've had no real structure to coding and logic. There have been attempts at structured programming and object approaches. We still have spaghetti code and spend billions on maintaining software. I've seen a number of fads and case tools, but the improvements have been marginal in my opinion. The fundamental structure of code, I call this spaghetti code, is still poor. How does one quantify improvements? Here's my answer in the form of a challenge. Compare your best approach to my approach. So again, here's the challenge test. Conform to the specification. Successfully complete the test matrix. The final test is enter negative pi, subtract from that negative 2.14159, hit equals, you should get a result. There are 18 entries in this final test. How many logic tests will your code make? Using traditional approaches, you can expect 90 plus logic tests. That is, 90 plus if-then-else, switch case, default type of structures in your program. The Software Engineering Institute teaches state machines in their TSP training program. There's a reference to this information down here at the bottom. In a proper state machine, the state transitions are all complete and orthogonal. Complete transitions, a transition is defined for every possible situation. Orthogonal transitions, none of the transitions have overlapping conditions. With a proper state machine, a next state is defined for every possible condition. The designated next state is unique. My comment, excuse me, the proper state machine is spatial, using if-then-else type code. The proper state machine doesn't know where it's working. I'll get into more detail why I'm saying that here shortly. The author said, and I quote, "Arriving at this state chart was definitely not trivial, and you shouldn't worry if you don't fully understand it. At the first reading, I wouldn't either." End quote. There are those that call for more and more abstraction. At some point in the engineering process, someone must provide the detail. The higher the level of abstraction, the more artistic license is available for the implementation. Conversely, the lower the level of abstraction, the higher the level of engineering detail. I'm not against abstraction, but too much abstraction has created many of the problems that I think software engineering has today. Here's what you get when the calculator state diagram is implemented in C++ by its author. This is a visual representation of spaghetti code. On the next slide, trace has been added for each routine. Adding trace creates even more complexity. This is a 1,000 plus line of code application. To truly display the logic requires nearly 20 additional calls to be added to the application. I'm talking about the logic when you run a test through this to understand what the trace is showing. I call this the breadcrumb problem. If you understand a little assembly language programming, this will probably give you a better perspective. Imagine a CPU without a program counter. The hardware would need to save states continually. That is, it would need to be dropping breadcrumbs. After an interrupt, determine where it was executing. That is, it would have to go back through that trail of breadcrumbs to figure out where it was. This represents massive amounts of logic as administrative overhead. Breadcrumb support would need to be built in. This is spatial logic. When an application that's processing a protocol exits for a next value, it leaves the application in a state. When the application returns with the next value, the application must determine through state testing where to continue executing. These are progressive applications processing event-driven protocols. This includes operating systems, financial systems, networks, compilers, real-time embedded systems, control systems, database systems, operating systems, and others. It's more difficult to find an application that is not protocol-driven. One example would be compute-bound weather models. These applications are driven by numeric algorithms. The program counter is a temporal pointer, so hardware is temporal. Spatial application software does not have an equivalent program counter. Traditional state machines were created to treat the symptom of no software program counter. The solution? Dropped breadcrumbs. Those are the states. We call these state machines. My solution? Create an application pointer. One time pointer for every engine table. The time pointer keeps track of application logic. The time pointer is always available for progressive protocol-based applications. The time pointer eliminates most breadcrumb logic. The temporal approach works for any kind of logic-intensive application. It does not preclude high-performance members, procedures, functions, method, or subroutines with loops. The temporal approach works with C, C++, Delphi to implement the logic in the temporal domain. The temporal state machine is event or non-event driven. States are true or false, and transitions are next true or next false. There are three fundamental parts: the engine with its time pointer, the logic tests, trace, and preemption control. The table is basically logic flow, and data flow are the reusable members. Logic flow is orthogonal to data flow, no control flow in the data manipulation, and no data manipulation in the control flow. The temporal state machine structure, there's an engine table relationship. The time pointer is a pointer into an array of rules and steps. And a table contains one or more rules. Each rule has a single entry point. Rules are like basic blocks. The structure of the array is it consists of rules which are made up of steps. Every step is a row. Every step is also a binary state. Each step has a test condition. Each step has a true behavior. Each step has a next rule or step. Each step has a false behavior. Each step has a next rule. Each step has a trace. So there are 7 elements in a traditional rule table. This is the fundamental temporal engineering structure: the engine, the logic flow, and the data flow. Trace can be turned on and off with dynamic binding. There can be sub-engines, with unique trace and the associated logic flow and data flow. The data flow controls when the engine is turned on and off. In 30 minutes, I can't teach temporal, but I can make you curious enough to take my challenge and learn for yourself the value of temporal engineering.